because the transient response of the system oftentimes can be well approximated by a reduced order model, and the advantage is that you have some simplification if it's reduced. Also, you have more insight into the model if it's a low order model. Second of all, or third, we already have analyzed first and second order systems, so higher order systems that can be approximated by first or second order systems, well, that's a good thing because we already have the information about first and second order systems. Okay. So the first thing what I'd like to show you is the case in which a
Sorry.
it's okay. Yeah, it's okay. The case in which we have a pole and a zero closely located. Okay, I'll go through that example, and I think I want to do it on, through the document camera. First of all, because that board doesn't erase easily, and second of all, I want to use MATLAB to show this. And so, I'll try it anyway. No. All right. I'll wait.
Professor, do you mind dimming the front lights also when
Okay. Well, yeah, I think I can put it over to lights. So. Is that okay?
Mm-hmm.
Start with this. So, our transfer function, we've got a transfer function h of s, and it's equal to s plus 5 over s plus 1 and s plus 5.1. So notice that the pole and the zero are pretty close together. Okay. And what we're going to do is approximate this transfer function. When the pole and the zero are close together, we can essentially cancel out those factors, the S plus 5 and the S plus 5.1. But the first thing we need to do is maintain the constant DC gain. In other words, if you take the limit as S goes to 0 here, you get 5 over 5.1. Okay? Now, if you want to maintain that same gain, what you can do is, in the numerator, what we'll do is factor out the 5. So you have 5, 1 plus S over 5. And in the denominator, you got the S plus 1. And here we'll factor out the 5.1. We got 1 plus S over 5.1. Okay. And so, in essence, what we're going to do is cancel these two out. But, you know, you say, well, that's not really, we shouldn't do that, right? But you'll see that by doing so, the resulting response to a step input will look much the same as that of the original. Okay. So this can be approximated by doing that. Okay. And so this is equal to 0.98 over S plus 1. So we're approximating the original transfer function by this. Okay. And what we're going to do is take a look at the step response in each case. Right. So, you know, you've got this transfer function here. We're going to apply a unit step function to that. And then we got this one here, call it H1 of S. H1 of S equals that. And so we're going to do the same thing. We're going to apply a unit step function. We're going to take a look at the response in each case. Okay, so let me just get the right one with me. And the right one is approximation 2. So down here, I go for x2. So I got approximation 2 there. And approximation 2. This is the little M file. Right? It basically defines a step response in each of those cases. And we'll just go ahead and look at the step response. And so this right here is a step response in each case. But what you notice is that they're basically, you can't distinguish one from the other. Oh, down here, it's supposed to be black and green. Down here, you can see a little bit of black, right? And in fact, the two terms, the two responses look like this. Like this here, you know, you can apply. This is a 1 over S there, and so you multiply this by 1 over S here, expand it into a sum of partial fractions, and then you take the inverse Laplace transform. Right? That's the kind of thing you've done before. Right. So the C of t is equal to 0.98 minus 0.98 e to the minus t minus 0.005 e to the minus 5.1 t. Okay, and in this case, the C of t is equal to 0.98 times 1 minus e to the minus t. So it looks like the first two terms here. Okay, and so this term here, you see, that's the other one that I plotted. That is really the only difference between the two. Notice one thing is that the coefficient, multiplying it is very small. is very small, right? And for that reason, you could expect it to not have much of an effect. And in fact, if you take a look at the figure that this one here, that's the 0.005 e to the minus 5.1 t. And you see that it basically disappears. Its effect is rather insignificant because it disappears very quickly, for 1 second, basically. Okay. Okay, so that you see how you can effectively cancel a pole and a zero that are closely matched, close together. And the next case we want to consider. First, want to draw a little diagram, and the diagram looks like this. You've got the S-plane. Okay, so this is the complex S-plane, the imaginary and real. Of course, this on the right-hand side of the J omega axis is the unstable region, right? So this is the unstable region. And over here is the stable region in the left half plane. And we're going to call that point there minus A. And this point here minus B, right? And you have, in this, generally, the ratio B to A is 5 or greater. Okay, I'll tell you the reason why in a second. But this is called the, these are, here you have dominant poles and zeros. Here to the left of B, you've got insignificant poles and zeros. Okay. See, the dominant poles here, they could be complex, conjugate, or they could be real, right? They give a transient response terms that are slow transient response terms. Like you saw that one there was rather fast transient response term there. And by slow, we mean they don't disappear very quickly, right? They have, and so you can say that they have a significant effect on the transient response. Okay. They're slow. Okay. Over here, the poles, insignificant poles, correspond to transient response terms that are fast. Okay. And they have an insignificant effect, because these terms disappear so quickly. They disappear quickly. Okay. So, I'll give another example here where you have which one do I want to give here? The zeros, the poles. Okay, so can somebody volunteer to get a big wad of paper towels that are real wet? And maybe a little bit of dry. So the next example, what we have is three transfer functions, right? We have, I called it T2 of S equals 1227.1 over. We've got an S plus 50, and then we have a quadratic factor here, S squared plus 4S plus 24.54. Okay, we have another one, T3 of S is equal to 245.42 over, this time it's S plus 10. The same quadratic factor over here, S squared plus 4S plus 24.54. And then the third, the T2, T3, and the T4 of S is equal to what is that? 73.626. 73.626 divided by, this time S plus 3, and the same quadratic factor, S squared plus 4S plus 24.54. Okay, so, and then let's notice where the poles are, right? So if I draw this here, we have a pole at minus 50, and then these poles here, if you solve the quadratic, what you'll get is minus 2, plus and minus j 2 square root of, no, it's 4.53. And down here, minus j, 4.53. Okay, so we have the real component. Yeah.
What's the value on T3 on the numerator?
The numerator, 245.5. Okay. 245.42. 245.42. 1227.1. 73.626. Okay. And notice one thing about the, let's put down the poles and zeros. So we have a pole at minus 3 here, so this is minus 2, so this would be minus 3. Thanks a lot. Appreciate it, yeah. Thank you. That's good. Okay, so where are the other poles? Minus, we have one minus 3. So I'll put that right about here. Yeah, these poles are there and there. These are complex conjugate poles, right? And then you've got another one here at minus 3. You've got one at minus 10. And you've got one out here at minus 50. So we have those poles, right, with the x's. And so the question is, which one of these transfer functions do you think can be well approximated by this T1 of S? T1 of S is equal to 24.54 divided by this quadratic S squared plus 4S plus 24.54. That's the question. Which one of these transfer functions here can be best approximated by this transfer function here?
T2, T3.
T3, right?
T3,
We pull out the 10.
T3,
No,
T3,
T3.
T3 at minus,
Factor out the 10.
is at minus 10, but notice this one is at minus 50, right? This one,
But this
sorry, right? Go ahead. The reasoning is that this pole is most, distant from this real component here. In fact, the ratio is what, 25? Okay, this one, it's 5, right? You know, what I said was that the ratio, when I drew that diagram, the ratio of B to A should be greater than or equal to 5. It is 5 for this case here, but it's 25 for this case here, right? So you would expect the response of this system here to be most closely matched to this. Okay, and see how do we go from one of these transfer functions to that one there? Well, we do it by like I did in the previous example, factor out the 50. If you factor out the 50, you've got 50, 1 plus S over 50. And essentially, we'll, instead of using that one, we'll use this. And what we'll do is just cancel that, throw it away. Throw it away. So what I'm saying, and then also 1227.1 over 50 is going to be 24.54. Okay? So in each case, as a matter of fact, the DC gain is the same. It's 24.54.
How is it that you were able to throw away that term?
I'm just saying,
Just
throw it away.
Oh.
That's the approximation.
okay.
Okay? And
Oh.
then we'll take a look at the response.
Okay.
Of each of these, as well as that one there.
All right.
Okay.
Oh, sorry. Also, where did you get the 2 is the term as well?
If you factor this,
Mhm.
the S1 and S2 are -2 plus and minus J 4.53.
Oh, okay.
Quadratic.
Mhm.
Okay.
All right. Thank you.
Okay. So let's take a look at that one. That one coded the crux second order response 1. And there it is right there. And if I execute that, all right, the T1 is the quadratic. Right, that's the blue here. That's the blue. The T2 is the red, and that's this one here that has its pole at -50. And so you see that the response of the second order system over there is most closely matched by that transfer function T2. Okay. So what we've done, we've gone from basically each of these is third order system. We've gone from a third order system to a second order system, so it's a simplified. Okay. So you see by just throwing this away here and getting the same DC gain, that has to be true in each case. The DC gain has to match. Okay. We see that the responses are pretty close to each other. These two responses here. Okay. This is T3 and T4. Yeah.
I guess I'm having trouble with just throwing that away for some reason. How are we going to know which ones to throw away?
Which row? You mean throw away this one or this one?
Correct. Yeah. How do we know?
Well, what I'm saying, you can do the same thing here. In other words, you can factor out the 3, or the the 3. So you have 1, 3, 1 plus S over 3, and here we have 10, 1 plus S over 10. So instead of using those, we can use these, and then we just throw these away, right? And the approximation, the second order approximation there is not as good for these two transfer functions as it is for this one, because this one has its pole most distant from the real component of the quadratic denominator poles. Do you see? Does that kind of answer your question?
Exactly. Thank you.
Yeah.
Say for instance, the numerators are not the same value. How would that affect this approximation?
It's independent of it.
Well, you have to arrange such that they are the same. Okay. So if they're somehow different, then the steady state step will have some error to it, right? It's not going to be 1. Okay. So if this DC gain is different here than it is there, then this in the steady state it will settle out to a small or something lower than 1. Okay, well it could be greater than 1, possibly as well. Does that answer your question?
Is there a way to compensate for that, or is this specific for when they're on the same DC gain?
Yeah, the way to compensate for it is to use a compensator. A control system compensator, integral type compensation actually would work to cause the to result in zero steady state step error. One more example here. This next is going to see, whereas here what we did was show the effect of an insignificant pole. We're able to throw it away in a sense, okay, while maintaining the same DC gain. Now what we're going to do is demonstrate an insignificant zero, okay? So we can take a look at this example here. We've got a t sub a of s is equal to 3s plus 3 over the quadratic s squared plus 2s plus 9. Okay, and then we have t sub b is equal to 1.8 s plus 5 over the same quadratic s squared plus 2s plus 9. And Tc is equal to 0.9 s plus 10 over s squared plus 2s plus 9. And so you see we can lay out the poles and zeros here. And so the quadratic has this pole at -1 plus and minus j2 square root of 2. So we have a pole there and a pole there. That's for the quadratic denominator. And then in the numerator, we have it at either -3, -5, or -10. So let's say -3, -5, and -10. And so those are zeros, right? Those are the zeros. And so -3, -5, and -10. And so the question is, which one of these transfer functions is most closely approximated by this t of s here, which is 9 over s squared plus 2s plus 9. Which one of those do you think? Which one of these three would be most closely approximated by that? Say that again.
Is it TC?
This, or this?
The third one.
Third one, okay. So with 0 at -10. So what we do here, if you want to come up with this approximation, you say, okay, this is approximately equal to, you say 0.9. What we're going to do is take out a 10, right? A 10, and so you have 1 plus s over 10, and then s squared plus 2s plus 9. And so we're going to throw this away. And we'll take a look at the resulting response, the step response of this system here, which is 9, which is the same as that, right? Over s squared plus 2s plus 9. Take a look at the response of this system and compare it to could, and compare it to the response of the original system, okay? TC. So, that was, two. And there it is. And if you execute it, what does it say? T of S is blue, right? It would be the closest response to it would be the purple one. The purple one is the word that has a 0 at -10. Okay. So these two responses are not too far off. Okay. Not too far off. So you can simplify this one. It has a finite 0 and 2 poles here to have simply 2 poles. So, yeah.
So if you were to do that same procedure for TCMS,
With what?
so for TCMS, we took out the 10 from that S plus 10. And we got
Yeah, this one here.
yeah, and we got 0.9 times 10 times 1 plus S over 10. And then we threw away that term.
Yeah.
If we were to perform that same procedure with the TB of this,
TB.
the only difference is you have 1 plus S over 5.
Right.
If you throw that away as well, you have the same answer.
You have the same answer, true, but what I'm saying is that this approximation, if you try to approximate this and this by that, it's not going to be all that great. Okay, because its zeros are closer to the pole there, the dominant pole there.
Okay, so it has everything to do with how close to the other.
How close the 0 is to the pole.
You said the general rule was the ratio should be greater than 5, greater than or equal to 5?
Yeah, the general rule, the ratio between the dominant pole
And the
and either the pole or 0 that we've been considering.
TB ratio equal to 5.
It could be,
It's like that's when the estimation starts to get
So
accurate.
that's like when it's not like
right, when
when it's
it's
still-
when it's just equal to 5, it may not be all that great. You know, you
but
can,
it'd still be acceptable.
it kind of, you know, that's where you have to play around with it a little bit. Okay.
Does it get more accurate as the further away you go?
These approximations
Mhm.
become more accurate as the polar 0
Right.
is a larger and larger distance
Okay.
away from the dominant pole.
Okay.
Okay.
Mhm.
So is it correct to say then from the graph you drew before with B and A, the dominant poles and zeros would be like before A, and insignificant poles and zeros are like after B, so then it makes sense.
Makes sense. Yeah, I can redraw that.
That would be helpful, thank you.
Huh?
Could you redraw it?
Yeah. Because I think maybe you missed it. You were not in the class when but here we said let that be minus A, and then here let that be minus B. And in this area here, this is the S plane. We have dominant poles and zeros. Dominant poles and zeros. Over here we have insignificant and zeros. Right, and so we said that if the transient, these dominant poles here correspond to the case where the transient is slow. The transient is slow, right? And for that reason, it doesn't disappear very quickly, and so in that sense, it's dominant, right? It's significant, right? So we have slow poles here, and here we have fast poles, fast poles. And so what we said was that this ratio B to A should be greater than or equal to 5. Of course, the greater it is, the better the approximation. Okay. So now what I'd like to do is start on the root locus, and start with an example that we did last week. Okay. We're working on that example kind of as a review for the exam, and just kind of introduce the root locus and what it is. So what we had was this system here. We had a gain, simple gain type of compensation. So I just put the gain together with the plant transfer function as one block. And then what we did was look at the range of gain K for stability. So for that, what we needed was the characteristic equation. And so the characteristic equation, it's a G, the transfer function is G over 1 plus GH. That's a closed loop transfer function. And the characteristic equation is obtained by setting the denominator here to 0. Okay, so 1 plus GH equals 0. In this case, H equals 1, and this is our G there. Okay, so this resulted in a cubic, right? Add 1 to the product GH, and so you get the S cubed plus 3S squared plus 3S plus 1 plus K. So then that's the constant term there. We formed the Ralph's array S cubed, S squared, S to the first and S to the 0. We put the coefficients 1, 3, and 1 plus K. And then we formed the new coefficient down here that was this product, and go this way, minus that product. So it's 9 minus K, 8 minus K. 8 minus K. And then we divide by this 3, but then we said, okay, to simplify it, we can always multiply through any row by a positive number and not without changing the conclusions. And so I'll multiply through by 3, and so I get this, because this entry here is 0. Okay, so now this entry down here, what you do is you take, just as we took this product, subtracted that product, this time we'll take this product and subtract that, which is 0, and then divide by this 8 minus K. And all that leaves is 1 plus K. Okay, and so we said that we must have no sign changes here. Okay, no sign changes. And what that means is that 8 minus K has to be greater than 0. We have to be careful in this, right? It's a greater than. And so what that means is that K has to be less than 8. And here, 1 plus K is greater than 0. It means K is greater than minus 1. K is greater than minus 1. So the range of gain K for stability is K between those that on that range. And then what we said was, in other, what do you get if k is just equal to 8? You get a a marginally stable system, right? With k equal to 8, the array becomes s cubed s squared. S to the 0. We get 1, 3, and 3, and with k equal to 8, that's 9. And then here we get a row of all zeros, and then this is 9 as well. Okay, and then so what we said was in order to we formed, and we counted row of all zeros, that allowed us to determine the case of marginal stability, possible marginal stability. We could do that by going to the previous row and forming the auxiliary equation, which is 3s squared plus 9 is equal to 0, or s squared plus 3 equals 0. That's the auxiliary equation there. And if you solve the auxiliary equation, you get s equals plus and minus j square root of 3. Right? Okay, and then if you just took this polynomial, auxiliary polynomial, and took its derivative, you got 2s. In other words, the derivative of this is 2s plus 0. And if you use these coefficients here in place of these coefficients, you could continue the array developments, right? So this then I replace it by 2, 0 replaced by 0, and then continue with the array development. Well, you still get a 9 down here, right? You get 2 times that minus 0 over 2, which is 9. Okay, and then what we again look at the number of sign changes. There are no sign changes. That means no right half plane roots of the characteristic equation, which means that there are no right half plane poles of the closed loop transfer function. That's a closed loop transfer function, C over R equals, that's C plus R. And so you see that if k is equal to 8, there will be j omega axis roots, and there will be no right half plane roots. Being a third order system, the third root has to be in the left half plane, and it has to be real because roots have to be, first order roots have to be real. And so we could say this: if this is the S plane, we have a pole at the we have for k equal to for k equal to 3, k equal to 8, we have a pole there. We have a pole there minus j square root of 3, k equals 8 there, right? And the third pole, you see, we could easily find the third pole because we have the characteristic equation here with k equal to 8. It's s cubed plus 3s squared plus 3s plus 1 plus k, which k equal to 8 makes it 9. And we know that one of the factors of that characteristic equation is s squared plus 3. So the third factor has to be a negative real value.
Is that s plus 9?
That's
S plus a?
S plus a.
Okay.
Yeah, and it's called a.
Okay.
So we see that 3a is equal to 9, equating corresponding coefficients. Right? You expand that out. The last term is 3a has to be equal to 9, so a has to be equal to 3, which means that the third pole has to be at minus 3 somewhere. Okay. And any questions about this now? Okay. And then also notice that no, I don't want to put an X there. I just want to put dot. Like this is for k equal to 8. Our third closed loop pole would be at -3 if k is equal to 8. And what you can kind of realize here is that as k changes, the closed loop poles change as well, right? The characteristic equation roots change. In fact, this is -1 here. That's where the 3 open loop transfer function poles are. Right? Remember, the open loop transfer function is GH, and that's just equal to k over s plus 1 cubed, right? So there are 3 poles there. 1, 2, 3, 1, 2, 3. Okay, at -1. It turns out that if you solve this quadratic, this cubic here, for values of gain k that start at 0 and increase on to infinity, what you would get in this particular example, you would get a straight line that goes like that. In other words, as the gain k increases, we can show the direction of increasing values of gain k. So, see, when k, see this point here would correspond to k equals 0. When k equals 0, notice that what you get is this, right? Which can be factored. Remember, it came from that, so it can be factored into s plus 1 cubed. So you have 3 poles at -1 when k is equal to 0. So there, that's the starting point of the root locus. As the gain k increases, and remember that the gain k is equal to 8 here at the when we have marginal stability. As the gain k increases, we'll have complex conjugate poles, and the third pole somewhere in here. Okay. As the gain k continues to increase, when it becomes 8, we'll have a pole there, and a pole there at -3. As the gain continues to increase beyond 8, we'll have a right half plane complex conjugate poles, and the third pole is moving further out. The third real pole is moving out. So this is what's called the root locus. Okay, what it is, it shows the movement of the closed loop transfer function poles as the gain k increases from 0 to infinity. From 0 to infinity. Okay. Now so basically you have this branch, you have that branch there, and this branch here, for this particular example. Okay, for other examples, it's going to be a little different. Okay, a little bit different looking. But are there any questions about this example here? Something you'd like to ask? Yeah.
What if k goes from 0 to negative infinity? Would the graph reverse direction?
Yeah. The graph. It reverses direction in some sense. Okay, but typically, when we consider the gain of the system, it's typically for positive values of gain k. Okay, even though in this case it's between -1, it can be negative here, right? But typically the gain it's an amplifier, right? And so the gain is made to be positive. Okay. So we would get in this case that. But if you have something like this, instead of that, say you had say s plus 1 and s plus 3. Okay. Then I'm not going to go through the whole thing here, but I just want to point out that the root locus plot, can be radically different for a different, open loop transfer function, right? And in this case, what's going to happen is we have a pole at the origin, we have a pole at -1, we have a pole at -3. There are no finite zeros. And it turns out, in this case, what the root locus is going to look like is going to exist on this range, it's going to exist on this range, and then it's going to, as the gain k increases, right, it moves along these arrows, the direction of these arrows. Right, so the roots move in, then they break away from the real axis, they eventually go into the left half plane as the gain k increases from 0 to infinity. So the root locus is not always made up of straight lines, that's what I want to say. Okay, here we have these curved lines. And in fact, what happens is that these will approach certain asymptotes, okay, which we're going to be talking about. Okay. What I want to do is start out with a simple example, and I'll just raise this down. An introductory example to the root locus. Yeah. We have k s plus 1 over s plus 3. And so what we like to do is plot the root locus. Now, the objective in this chapter is to be able to plot the root locus without explicitly solving for the poles. Right? We want to do. In fact, you'll see that we can plot the root locus using a set of rules, right? And we don't explicitly solve the characteristic equation for various values of the gain k, but in this introductory example, I will do that, and then we'll kind of move towards being able to do it by applying these applying these rules, okay? Root locus construction rules. So the graphical root locus construction rules. So let's first find the closed loop transfer function, or if you wish, the characteristic equation. Remember, the characteristic equation is 1 plus the open loop transfer function, 1 plus g, set it equal to 0, right? And so in this case, then we have 1 plus k s plus 1 over s plus 3 equal to 0. So we get s squared plus 3s. So we can bring together the k and the s. So we have this is ks, k plus 3, right? S plus k equals 0. So that's the characteristic equation. If you solve that, what you get is an S1 and an S2. S1, S2 is equal to, solve the quadratic. You've got minus k plus 3 plus and minus the square root of b squared minus 4. Right, so you get k squared plus 2k plus 9. Okay, divided by k plus by 2. Right. So let's make a little table. Make a table here. Okay. S1 and S2. So we have k. Let k take on values starting at 0. Starting at 0. okay? And going towards infinity. So we'll look at the 0, 4 thirds, 5, half. The reason I took these particular points is that they gave nice values for the roots. Okay, 7 and 100 and 1,000, and then values of k that go towards infinity. Okay, for S1, you get 0, then you get minus 1/3. And the S2 is minus 3. In other words, when k is equal to 0, you get 0 and minus 3. You can see that right from here. When k equals 0, you get s squared plus 3s plus 0, right? So 0 and minus 3. Okay, and then with 4 thirds, we've got minus 1/3 and minus 4. And then we have minus 1/2 and minus 5. And then minus 0.76 and minus 9.24. That's 9.24. And then minus 0.98 and minus 102. Right? And then minus 0.998 and minus 1002. And then as k goes to infinity, this will go towards minus 1, and the other root will go towards minus infinity. You see, we can work with this here. Right? If you take the limit as, what we'll do is divide both sides by k. So you have 1 over k plus s plus 1 over s plus 3 is equal to 0. So I just divided by k, right? And now I'll take the limit as k gets large, this, right? And so this term goes away, and so all you're left with is s plus 1 over s plus 3 equals 0. And so you get basically s, you got, we have, we're going to have, I don't want to simplify that yet, but what we have is 1 0 at minus 1, and we also have a 0. This is 0 with the be 0 when the magnitude of s becomes infinite, right? Because you have, basically you have, if s is really large, you have s over s squared, and so that's 1 over s. So when the magnitude becomes very large, this becomes 0. So you have one finite 0 at minus 1, and then you have another 0 at minus infinity, when s, in this case, is minus infinity. Okay, so let's plot these. Okay, if you plot them, we're going to get the root locus. And so here is our real axis. Notice that all of these roots here, all these roots are real, right? And so they're, in fact, they're negative real, right? So the root locus will exist only along the negative real axis. Okay, and let's consider the roots s1 as k takes on these values. It goes from 0, minus 1/3, minus 1/2, minus 0.98, 0.998. So clearly, it's as k goes from 0 to infinity, the root is going from 0 to minus 1. Right? So remember you had a pole at the origin. The open loop transform pole at the origin, and a pole at minus 3, and 0 at minus 1. a 0 at -1. So, oh, sorry.
That's right.
As the gain k increases from 0 to infinity, we have the roots going from 0 to -1. And so,
Yeah, sorry.
it's okay. But this shows the direction of the roots as the gain k increases from 0 to infinity. Here, k equals 0. There, k equals infinity. Okay. And this is one branch of the root locus with this direction indicated. And then the other roots go from -3 to -infinity, right? As the gain k goes from 0. Say, break the axis here. At this point is -infinity, and that corresponds to k equals infinity. Okay. So all I did, and so this make it bold here to show that this is one branch of the root locus, and this arrow there shows the direction of the roots as the gain k increases from 0 to infinity. So this here is a complete root locus for the system. Yeah.
So root locus is like a diagram explaining what's happening, right?
Yeah.
Okay.
And it basically, the root locus, it shows you the movement
Mhm.
of the closed loop transfer function poles
Okay.
as the gain k increases from 0 to infinity.
Okay.
Right? And notice that the poles are always in the left half plane.
Because that's when it's stable, right?
Yeah, the system is stable for positive values of gain k.
But in the other example, it was unstable, correct? As k.
When k it went beyond 8,
Mm-hmm.
you had an unstable system. Right? So here, you see this root locus allows us to make certain conclusions. This is the root locus plot diagram. Allows us to make certain conclusions about the stability of the system. So we're not continuously involved with explicitly finding roots of the characteristic equation. We'll be able to graphically use some graphical root locus construction rules to make to draw the root locus. Oh, and so what I want to do here, Leslie, is put down some basic rules, root locus construction rules that apply to all cases, not just this case here. So root locus construction rules. Now, this is not a complete set of rules, but it gets us started, right? So the first one is that the root locus always begins at the open loop transfer function poles, right? Begins, what does that mean? K equals 0. The root locus begins at the open loop transfer function poles. Right? We have a pole at the origin, a pole at -3, right? So the root locus always begins at the open loop transfer function poles. Okay, OLTF. Poles. Begins, meaning k equals 0. Second, where does the root locus terminate? Right?
K equals infinity.
At infinity, at the open loop transfer function zeros. The root locus always terminates, and that means K is infinite at the open loop transfer function zeros. Okay, the third one, the branches. And in this particular case, we have two branches. That's one here, that's another one here. This one here has three branches. 1, 2, 3. Okay. The other system that we had, the K over S plus 1, S plus 3, remember that one, what the root locus looked like was here, here, and here. For low values of gain K, we have one branch here, second branch here, and a third branch here. If the gain K increases further, we have one branch there, second branch there, and a third branch again along the negative real axis. Okay? So just to give you try to understand what we mean by branches, right? But the branches are always directed from directed from open loop transfer function poles towards open loop transfer function zeros. And these zeros are finite as well as infinite. And the last one, number 4, the number, that's number, right, of branches is equal to the order of the open loop transfer function. The number of branches is equal to the order of the open loop transfer function. In this particular example, the order is 2. We have 2 branches, one branch here and one branch there. Okay, this system here, third order, 3 branches. This system here, third order, 3 branches. Okay, so these are root locus construction rules that apply to any root locus, and we'll add to that next time.